In the previous session, we looked at the effects of aliasing, and because of aliasing, there will be an error. And we tried to quantify the error, and we actually derived an equation which gives us an idea about what is the maximum possibility of the error. So epsilon is the error, which should be lesser than uh, twice the integral magnitude of the g of f dx. This is what we had derived in the previous case. Okay, so now we'll be moving ahead from that. So the next step is to study about the procedure of sampling. This is sampling procedure. So in this, we are going to look at the action plan for sampling the signal which is not strictly band limited. Okay, so we know the meaning of band limited. We know that what is the maximum frequency content of that signal, right? If we specifically say that, yes, so that is equal to capital W hertz, then we call it as, yeah, this particular wave or this particular signal is band limited. But now we are looking at the sampling procedure of a non-band limited signal. Okay, so in general, when you say it is not band limited, ideally speaking, signals amplitude spectrum is right is not fixed to any bandwidth, right? It can be outside the bandwidth. Okay, you can say that it can be even infinite bandwidth. Doesn't matter. Okay, well, when we have such signal in place, right? What should be the procedure we should follow to sample it out? All right, so that's what is the sampling procedure is all. Okay, right, so here we are trying to look at the concept wherein, right, this is sampling procedure. I'll write here itself. This is for the sampling of any signal sampling of any signal which is not strictly band limited. So when I say it's non-strictly band limited, right, this can actually imply that the signal may have a large or right non-finite. Okay, it's a large or non-finite bandwidth. This is a possibility. So now when we say this is a possible case, now we have variety of options possible, right, in terms of the signals characteristics. So we'll explore that and we'll try to make a rule using which we try to sample. Okay, so the general step is that before sampling, the signal has to be passed through a low pass filter, right? Just to make sure that, right, you don't have a frequency outside a specific band, right? This is absolutely necessary because until and unless you know that, you cannot go with the sampling. Randomly, if I choose a sampling rate, what happens, right? If the signal exceeds the certain frequencies, then there will be aliasing, correct? Right. So just to avoid that, we try to go ahead and make sure that, right, there is a maximum frequency content, right, in the signal, right? So we'll try to do this first. So this is, say, I can say, right, step by step. So step number one. Okay, so this is before sampling the signal. The signal must be passed through a low pass filter, right? So there is a specific name for this because we are trying to restrict the frequencies uh, of the signal to a limit. The limit is required because if it exceeds the limit, there may be a possibility of getting aliasing frequencies, right? We know what are aliasing frequencies of a given signal, right? So we want to avoid that. So just for that reason, we try to put a limit over there. So since this particular filter, low pass filter, is going to put a limit over there, it's also called as the anti-aliasing filter. Okay, so I'll try to name in the bracket. So this is anti-aliasing filter. Right. This is used to remove the high frequency component. Right, I'll write a components because this also includes the noisy part, right? Noise is belonging to a character. Noise has a characteristic whose frequency will be very high. That's one characteristic of the noise, right? It's also doing a serving as a dual purpose for us. One, it actually eliminates the higher frequencies of the signal, and the second part is that it tries to eliminate the noisy components. Or right, so high frequency components, right? That are normally, if it is a signal's integral part, right, whatever frequency, high frequency we are talking about, if it belongs to the, or if it is an integral part of the signal, right, then I cannot eliminate. But now what I'm trying to do, I'm trying to eliminate the high frequency component that are not the essential uh, part of the signals. All right, so high frequency components that not the essential part, not that are not essential of the signal. So we try to eliminate all signals, right? So after this, what after this filtering, right? We expect the signal to be strictly band limited. Okay, so let's try to uh, plot it, right? Anyway, we know that we already have plotted such spectrum few times, and now what we are plotting is a copy of that. That's all. Okay, so let's say this is the frequency axis. This is a magnitude. So I'm trying to plot the magnitude spectrum. So magnitude G of f. So this is how it looks like. Okay, so this is band limited signal. There is a maximum frequency content of up to plus or minus W. Okay, so this is the G of 0 part. Right. So once you band limit your signal to a certain limit, this is how it's going to look like. It's just an example, right? Even we can write a any other shape of the waveform here, right? That's fine, but it should be within plus or minus that. Okay. So once this is Okay, once the filtered signal is obtained, right, let's call this, since I am marking this as g of f in the time domain, this should be small letter g of t. That's the representation, correct? Okay, so the filtered signal is now going to be sampled using the train of impulses, right? Normally we call it as a Dirac-Coombe, right, of a certain frequency. The sampling frequency should be twice at least, right? The twice of this W, or you can even call it as a cutoff signal, right? We use that word now when we explain. So can I think I can write this as a step number two, right? The filter signal g of t is then sampled using a train of impulses. So there is a name for it. So that is known as the Dirac-Coombe function, right? With sampling rate. What's the sampling rate? We denote it as Fs greater than or equal to 2W. Right here we have a specific value for W. It is called as the cutoff frequency. Cutoff frequency. Again, we obtain this W not because of the characteristic of the signal, but this is a characteristic of the low pass filter or the anti-aliasing filter we used. So this W is the cutoff frequency of that filter. Okay, so cutoff frequency of the anti-aliasing filter. Right. Now, so if at all I try to do as the sampling at a higher rate. So higher rate in the sense whenever the Fs is much greater than the 2W, we have a specific word over there that is called as the uh, oversampling. Okay, you are doing more than the required samples. Correct? You are trying to extract more samples than required. The ideally required case is Fs is slightly greater than 2W. If whenever it exceeds, we call it as the oversampling. Right. Now, what happens? We know that whenever I try to exceed the Fs, right, whenever I try to make the Fs much greater than 2W, right, I know that whenever I try to do the reconstruction, right, whenever I try to perform the reconstruction of the G of F from G delta of F, I'm going to get more gap between the spectrum, right? So this actually brings what is called as a guard band in place. So between the two triangles I'm going to get on the frequency side, I will be having more and more space. So let me show you what I mean. Anyway, I'm going to write that in, but let's quickly go back and understand what I meant when I said oversampling and the effect of oversampling. So this is the ideal sampling, exactly touching each other. But then when I move up, you can see that there is a Fs much greater than 2W. So you can see that there is a gap between the right replica or the copies of the spectrum, right? So that is the result of Fs being much greater than 2W, right? So now I am talking about this condition. Okay, so I'll write that in sentence over here. So anyway, the two steps we should be following to do the sampling or a sampling procedure is over. Right now we are discussing about that. So what are the various options we have? Okay, so the first one is like this. So if at all we try to do the oversampling, Oversampling. What do you mean by oversampling? I write in bracket. The FS sampling is much larger than the 2W. Okay, oversampling the signal. So the signal is, I'll write in the time domain itself. So that is, I can write it as say g of, it is g of t, right? Oversampling the signal g of t helps the reconstruction. So there is a reconstruction filter, correct? So we are talking about that now. So the reconstruction filter to suppress the spectral, the copies, right? The copies of the main triangle, we call it as a spectral replicate. It means it's a copy located at a different spectra, right? So multiple frequencies will contain the same triangle copied all the way, right? So that's what is spectral replicates or spectral copies, right? So there is a mathematical equation for that, right? So it is actually capital G of f minus n fs, and n varying from minus infinity to infinity. That's what we are talking about. So spectral replicates. There is an amplitude fs into capital G of n minus, not n, sorry, f minus n fs. So f is my, it's a frequency axis, so I should use the variable f minus n times the sampling frequency. So this is the equation of that spectral replicates. So all these, right, are present, and we try to eliminate them whenever we go with the frequency that is much larger than the required, right? So I need to use a 2W or slightly more than 2W, but when you can definitely increase this. It's not going to cause any problem to us, but it actually moves our spectral values to the locations which are far. So let's try to look at that now. So this is the f axis. Maybe somewhere in the center I have this is the G delta of f sampled signals spectrum. Okay, so we have to have several copies of the original triangle which we wrote. So I can see that it is the replicate, right? So the central frequency is 0. This is plus W. This will be minus W. Now the sampling frequency, sorry, the sampling frequency fs has been chosen in such a way that this is much greater than 2W. So anyway, the lower sample, that is fs minus W, will not collide or coincide with the W, or there is no overlap. Okay, so this is fs plus W. Fs plus W. I have the negative frequency minus fs. So this is minus fs plus W minus fs minus W. So the highest amplitude will become now fs into the G of C. So there is a scaling factor coming into picture like this. Right. Now, you see, because of this guard band, we have some advantages now, right? So, whenever I try to go for a reconstruction filter, right? So, reconstruction filter is the one which converts the samples or the sample signal back into the continuous signal. Okay, so I think I can show you one diagram representing the reconstruction filter. So we had one, yeah, you see, there is a G of n by 2W, which is the input, and there is ideal low pass filter. So this itself is what we are going to call as the reconstruction. I like the word here. Reconstruction filter, which actually generates the G of t back from the samples. Right? So we already have seen that this is what is a spectrum. I'm expecting the spectrum just like this. So its actually amplitude is 1, right? From minus W to plus W. And as soon as it's outside the minus W or plus W, it should reduce to 0. So there is a sharp cutoff, right? You can see that amplitude all of a sudden falls to 0 on both the sides. This is what is the ideal characteristic of the filter, right? The reconstruction filter, which we are talking about, right? Which we are talking about now. Okay, but now because of oversampling, I have some advantages. So the advantage is like, see, I actually have, okay, I'll even write the guard band. Sorry, I missed that. So let me write the guard bands over here. So this is actually the advantage. So I need to write about the guard. So that is the guard band. So can you guess what is the advantage of having the guard bands like this? Will it provide uh, anything, any help? Yeah, correct. So there is a separation between the frequencies, correct? So because of which, is there any advantage specifically with respect to the reconstruction filter, which we discussed just now? So ideally, what is expected, I'll write now. So this is the ideal response of the filter, correct? So whatever you see in the red color, this is what I'm expecting as an ideal uh, ideal reconstruction filter, right? That was we were expecting like this, thinking that there maybe you just sample the signal at 2W, correct? But it is not 2W now. Actually, we try to sample it at a much higher frequency, because of which I brought a guard band. All right. So anyway, we have a guard band now. So because of this, is there any relaxation uh, towards the way you design your reconstruction filter? Anything towards that? So maybe I'm expecting an answer from your DSP concepts. Recall the filter design, maybe FIR, whatever, or even the varieties of filters of different orders you might have studied, right? Anything you can try to recall and try to answer here. The question is specifically towards the uh, DSP aspects of the filter design. So ideal filter, which we discussed just now, right? So the rectangular pulse shaped frequency response. Is it possible to design? Can you recall from the DSP? If I want to have a sharp cutoff, what is the requirement? If I want to design sharp cutoff, very sharp at W, I want till then it is 0. All of a sudden, I want it to raise to the highest value, and at plus W, I want all of them to it should be reduced to the lowest value. That's a 0, right? So is it possible, or right? First question, maybe definitely answer is yes, because we have tools. Tools can definitely design this. What's the implementation side of that? Is it possible to implement that on a hardware or anywhere? If you want to implement a filter of very sharp cutoff, what are the requirements? Or how do you represent such a filter in terms of a transfer function or anything, any input you can give? I can expand on. Just try to recall what you have said. So first, let me tell you a concept that is called as a roll off rate, right? Then we'll come back. No problem. Okay, so let's consider that there is a filter. I'll write only one side of the filter. Okay, so uh, again, ideally talking, right? Your filter's response is expected something like this. I'll try to draw the ideal response now. So this is an ideal filter. Okay, when I say that low pass filter, I'm expecting a sharp cutoff like this. Okay, at a W hertz, I want this to be 0 until W, starting from 0 hertz till W hertz. I want, right, its amplitude to be 1. This is the ideal case. Okay, when you come to the practical case, what happens? If you remember, the practical case will be slightly different, right? Normally, you may have the amplitude which is very closer to the required value. This is fine, right? It might come till here. But then you see, right? Will you write a straight line downwards? No, it will slightly move like this, correct? Are you okay? So this is the practical what you call, right? The practical filter. This actually moves out, right? And this how quickly it, right, comes to 0, right, is what is called as the roll of rate, right? How quickly. So now you see, if I want this to be very quick, right, if this I want this to be very quick, it has to come down like this, correct? This is a faster roll, right? So this means, my question now, I'll change my question what I asked earlier. So I gave example first, second, third and high order. So will you increase the order or decrease the order? So this is a lower roll of rate. Now I see this is a higher roll of rate because it is faster, correct? It comes down faster from 1 to 0. This comes faster roll off. So, right, for a slower or a lower roll off rate, can you repeat, please? Sorry, I couldn't hear you. So now you can compare this ideal filter which is there here, right? This is the highest possible roll off rate, correct? So I can actually call it as the roll off rate, right, is highest. So which one you expect to have the highest order of the filter? Whose order should be highest? As the order increases, right? Yeah, this becomes faster. So that's why you need to go for a higher order filter. Right, now you recall the concepts which we studied in DSP, right? If you want to go for a higher order filter, right, for this purpose, I want to achieve a higher roll-off rate. So for that reason, I'll try to, right, make the filter more complicated by increasing the order, right? Okay, equation becomes bigger. There are more powers of your, if you are doing it in the, what do you call it, using the Laplace transform, let's say, so, the s term will be more, right? S to the power 4 is a fourth order. If you have s to the power 5 in the denominator, that becomes fifth order function, and so on. So the system becomes more and more complicated. That's the first thing, right? And because of which, even the hardware implementation of that becomes very difficult. Okay, so that's what is the case. That's why I brought this concept now. Now you recall. So if at all I wanted to design a filter which is having very sharp cutoff like this, right? That would have been very difficult because this will have a very high order. The order of the filter or n value will be very high. But you see, now I have a guard band. I don't have to worry about that. I don't need this sharp cutoff. I can even make this like this, right? So which is actually simpler design because there is a guard band in the middle, right? It's not going to get affected at all, right? So nothing is there in the guard band. You don't have anything, right? So that means yes, what I can do instead of designing the filter in a very complicated way or making things difficult for analysis, implementation, etc., right? You can simply design a filter, right, which has a practical response. Practical response in the sense it has to have a flat top at the right at the highest position or the peak. Then you can have a slightly like this. So this is the most suitable wave shape of the filter. This is possible because on both the sides you have guard bands, correct? So because of having the guard bands, that's the advantage, right? I don't have to design a filter of very high order, getting a very sharp, right, frequency response like that. I can even go with the response which is like this. And what is the highest value that you can reach? What is in the sense I'm talking about this particular value. What is this? It can even touch the next value, right? The next triangle if you recall, right? So this value should be fs minus w. So ideally, this is the practical one, right? The blue colored one, which we have drawn here, is the ideal is a practical one. I can even touch this as fs minus w. Until there, you can design. So right, this portion is what is called as the that's the advantage of the guard band. Okay, what I do, I'll try to this actually become if I write here it's more messy. I'll try to draw again. Only that the practical filter that part. So this is the magnitude response of the filter. Say it starts like this. I'll try to draw a more and more practical. So somewhere here, this is the part which I want to pass. This is going to maintain the highest value, and this next part will be like this. So let me try to do this. So this is the reconstruction filter. So we denoted that as h of f, magnitude h of f, amplitude being 1 over fs, because there is a fs over there. When I multiply by 1 by fs, it becomes equal to 1, right? So because of that, so I'm trying to write this part that is equal to 1 by fs. Okay. Now, so this is 0 is w. This can be the highest possible value, which is fs minus w. So this is f. So let's try to denote the characteristics of the filter over here. So whatever the filter passes is called as a pass band, right? Then you have a transition band, and right now we are going to call the transition band as the guard band. Okay, and outside the guard band, whatever frequencies that exist and the filter is not going to pass that, we'll call it as by the default name, that is a stop band. Okay, so which is this? This is the pass band of the filter. Then we have what is called as guard band in this case, but generally this is called as the transition band, where the pass band to stop band transition takes place in the filter's response. And after the stop band, sorry, after the guard band, we get the stop band where the amplitude reduces to, or amplitude is close to zero. So, the magnitude response of the practical reconstruction filter is like this. All right. So, this is the one, this region is what is has been made convenient to us because of the presence of the guard band. I'll write this is the roll off portion, right? Otherwise, this has to be very sharp. Now it is very fine. So we'll write another point here from the magnitude response of the reconstruction filter. So we have the following specification we could understand, right? There is a pulse band, right, between 0 lesser than frequency lesser than W, right? So normally in this particular pass band, what is the value of the gain? Gain should be 1 by Fs, right? This is because the message has a value of gain that is equal to Fs. So Fs into this 1 by Fs gets cancelled and you get your 1 back. Whatever is the g of 0 will come back because of that, right? So passband of this with gain equal to 1 by Fs, right? So I'll write the reason here. This is because the g delta of f has gain. Okay, it's not called as a gain. I can call it as a magnitude. That's a more appropriate term. Has a magnitude of Fs into g of 0 at f equal to 0, right? And to get g of 0, right, we need to cancel the Fs. So Fs is there, I need to cancel. So what you do in order to cancel that, multiply by 1 by Fs, f of 1 by Fs. Sorry. Okay, so that's what we have done now. So that's how we decided what should be the amplitude. So even in the spectrum we wrote earlier, right? Sorry, the frequency response of the filter, I'm multiplying by 1 by Fs, right? That's the highest frequency present. So after this pass band, now you can see that what's the next band we have. So after this pass band, now I have a transition band, right? With the guard band inside that. So the, this has a guard band with roll of characteristics that extends from W lesser than or equal to the frequency lesser than or equal to Fs minus W, right? Outside this particular band, we have what is called as the stop band. What's the condition for stop band? All the frequencies, that is F, any frequency F which is bigger than the uh, Fs minus W. Outside this, whatever we call, it belongs to what is called as the stop band of the filter. So this is the procedure we are going to follow for any signal that has uh, non-limited bandwidth, right? Bandwidth is not limited, so you decide what is the ideal characteristic, that ideal frequency content that you need in that particular signal, right? For example, let's take an example of a speech. Okay, so speech signal generates frequencies anywhere in the region 0 to 3.5 kilohertz generally, or even some of the voices will touch the 4 kilohertz range. Okay. But when the mic records something, right, it picks up everything, including the noise from the background. That can be from the phone, some music playing at the background. Music will go even up to 20 kilohertz. Okay, so that's why the CD quality of audio is 44 kilohertz when you sample it out, right? That's because it's not just voice; it's also in the music, right? So that's the thing. So if your communication is just say voice communication like telephone, you don't need to sample at a very high rate. You can sample it at 8 kilohertz. That's enough because 8 kilohertz carries every information up to 4 kilohertz, right? So you use the sampling rate of 8 kilohertz. So up to 4 kilohertz, everything is covered, right? So that was what being used in the telephonic system, right? Where the wired communication used to take place, right? Earlier days. So that's an example, right? Whenever you try to capture the voice from the uh, the the mic, right? It actually picks up everything. The background noise, if there is a rain, it captures that, right? So somebody playing music will get that also gets recorded. Somebody else doing some other noises, right? Everything will be captured. So you don't want them to be you don't want to transfer that, right? So what you do, you put a filter inside, right? That limits your frequency contents to only 4 kilohertz. So definitely that 4 kilohertz contains everything related to the voice of the person who is speaking, right? So that is represented. Outside 4 kilohertz, everything is eliminated. So you don't capture noise, no background noise, etc. will be directly eliminated, right? So because of that, you will be able to send, right, the signal in this response. And on the other side, the reconstruction filter can be designed in this way, right? So you get a guard band in the middle. So because of that, on the other side, whenever, right, somebody wants to hear what has been sent from the other side, they can use a filter like this, right? So using the sampling rate, you decide what is fs, take 1 by fs into as an amplitude of that particular filter, which you design on the other side to get back your original signal back, so that whoever is present on the other side can hear it. Okay, so that's the actual practical use of what we have